Okay, what you're looking at here is a large-scale demonstration of how an optical fibre works. There's a laser at one end shining red light into this perspex tube, which is flexible, so you can see that even though I move the tube around, the light is trapped in the fibre. My name's John Harvey. I've been doing research on lasers and their application, in particular fibre optics, at the University of Auckland here now for over 2 decades. Real optical fibres, of course, are much smaller than this. You'll see there's one here. This is a roll of optical fibre. It's about 125 microns in diameter, about the same as the diameter of a human hair. And this spool contains 15 kilometres of optical fibre. It's very pure glass, but it's very small. The most obvious use these days of optical fibres is in the field of optical communications. Optical communications, optical fibre communications, have largely displaced traditional methods of transmitting information. If we go back, perhaps even just to 20 years to when I started working in this area, telecom was still using cables like this. This is a 400 pair, twisted pair cable which will carry 400 telephone conversations to 400 homes. In contrast, this optical fibre here, small as it is, will carry not just 1,000 or 1,000,000, but perhaps 1,000 million telephone conversations simultaneously. When you go and buy your goods at the grocery or the supermarket, you may have noticed that it gets swiped past a reading station. Those reading stations all involve lasers, as does your DVD player and many, many other devices where the laser itself is not apparent, but they're pervasive in society now. The most obvious and extensive use of them is in communications, and here at Auckland we have been concentrating our work on research concerning fibre optics. Nevertheless, there are a lot of other research areas that we've worked in which involve lasers being used in ways which take advantage of their particular characteristics. One of the most interesting situations where a laser was used here dates back 20 years to the time of the Rainbow Warrior bombing, when the police approached us and said could they use the newly developed technique of laser fingerprint detection, which had not at that time been used in New Zealand. That work was done here in this lab and it was extremely successful. A superb print was obtained from a chart which came off the yacht Ouvea, which brought the bombers to New Zealand, and the print was that of Alain Marfart, who was subsequently convicted of manslaughter. That led to the use of laser fingerprint detection here for a significant number of years. That involves the technique of using lasers to generate fluorescence, and that has a lot of applications in biophotonics and biological sciences research. One of the important areas of research for us here in this lab is the characterization of very short optical pulses, the pulses that are used in very high-speed optical communication systems. These pulses are so short that no conventional electronic technique can actually measure their characteristics. We developed for that purpose a special piece of apparatus which you can see here. This is one of the original experimental setups. There are lots of mirrors, beam splitters, detectors and things here, and a spectrometer. As one of these mirrors moves, the spectrum is collected, and that results in a two-dimensional plot that you can see here on the screen. From this screen we can determine all the characteristics of the pulse. We found that this was so valuable that lots of other people asked us to build these, and therefore we came to the conclusion that it would be a good idea to form a startup company to actually develop those. And these instruments based on this technology and a newer technology are now sold around the world.
Hi, my name's Doug Reed. I'm a PhD student here at Auckland University, and I also work as a research engineer for Southern Photonics. One of the things I work on is trying to get our instrument into small boxes. The bottom box here is our original box that we used to put our apparatus in, and the top top box here is the much smaller and slimline new version that we're trying to work on. It's also hoped that the new instrument will be real time, so to give us real updates of the pulse as it changes. Over here is what actually goes inside the box. It's pretty complicated, but it's got a lot of optical fibres. These fibres here transmit the light that we're trying to measure, as well as lots of electrical cables, which is a bit of a mess, and also RF cables, which transmit high frequency radio signals. Okay, all those work together to give us an image of the pulse in real time. The way it does that is by turning the light on and off really, really fast using an electro-absorption modulator, which is this little doodacky here. And from after that, it resolves the colours that make up the pulse using a fast filter, which is one of these things here. The pulses that go into that machine are generated from this machine here, which we also built. This is a pulse source that generates pulses at 10,000 million pulses a second, which is pretty quick. And the pulses are only 15 millionths of a second long. So that's why we need a fairly high-tech piece of machinery to measure them with. So what I'll do is I'll take you over to the screen where we'll show it working. The way we control our instrument is using a computer interface. And the computer interface has two lots of information. One is time, what the pulse looks like in time, as well as what colours make up the pulse. So if we look at the screen, this picture here is a snapshot of a pulse. Where here, along here, we have time information, and here we have frequency or colour information. So every time the screen is updating here, we are taking a snapshot of what the pulse looks like. Here at Auckland University, we're trying to take new measurements and do new techniques all the time, and that's really exciting because we get to take measurements that no one else in the world has done yet, and make new ground with this technology all the time. And the reason we're trying to do that is to make your internet faster and to make the connections between countries faster. With this technology, we're hoping to make those connections 4 or even 8 times faster than they are today.